Good morning. All right, today we are going to start on chapter 19. We'll see how far we get into it. I think we're going to cover most of the reactions today and probably finish them up on Friday. There will be a tornado drill at around 11, so you guys can just stay in your seats during that. That is apparently the most safe place to be in this building. All right, so let's get started on chapter 19. I'm going to briefly cover the nomenclature. There's not going to be nomenclature on this exam. We're instead going to do that aromatic versus anti-aromatic thing that was on exam 2 practice. I'm still going to cover this just so you guys have a general sense of it. So typically, if we have just carbons, this here would be heptane. If I had an alcohol, so this here would be 2-heptanol. OL being our suffix here. If we have an aldehyde, AL will end up being our suffix. So this here, we have 7 carbons and an aldehyde at the end. This is going to be hept and al, so AL for aldehyde. For ketone, our suffix is going to be -one. So taking the same molecule, putting a ketone here, this would be 2 hept and -one. So ONE for ketone. Okay, so that's nomenclature for this section. The rest of it follows just normal rules. We are going to talk about a series of reactions today, which all have a very similar mechanism to them. They're all going to deal with an aldehyde or a ketone. So if I take acetone here, which is going to be the molecule used for most of these, and I throw an H+. Okay. This happened at the beginning of last class too. Not sure what's going on there. H+, H2O. We are going to pick up this proton. That is really gross. All right. Someone is has a mic on. All right. So we picked up this H+ here. From this point, water can come in. Attack our carbonyl, kick these electrons off. We're going to generate a diol. Kick off this last proton to another water and make what's called gem diols, where both of our oxygens are on the same position here. This is also reversible, so you can go back in the other direction. For a lot of the reactions we're going to talk about today, if you want to take them off, this is going to be the way to do it, is just throwing an H+ and H2O, and it'll let you kick out whatever you have. Okay, so if we take ethanol instead, it's going to complicate things a little bit more. Starting with my carbonyl here, throwing in H plus, ethanol. All these reactions are going to start the exact same way. We're always going to pick up a proton. Protonate this carbonyl here. From this point,
I barely knew collisions. I did 3 and I was just like, this is ridiculously easy.
Yeah. 3, that was like literally the most basic collision problem. Like
That was
you could
something
get.
I would have done in high school. I mean,
Yeah.
I would have understood completely. So I was just looking at that. Like originally, I was scared.
not like a student, right? I don't think so. All right. I'll say I don't think they're wired into the system anywhere. So if we have this ethanol here, this can attack at our carbonyl. Yeah, but they shouldn't be going. Someone asked in the chat if it was a student unmuting, but I don't think they are actually wired into the whole system. Okay. Right, ethanol attacks. We're gonna make OH protonated version of this ether here. We can pick up a proton. With another ethanol. And we're gonna make what's called a hemiacetal. And I'll talk about when you see what a full acetal is, a hemiacetal makes sense. It's essentially just half of an acetal here. Our next step is this other oxygen to pick up that proton we just lost. We can lose water. Another alcohol can attack. We're going to make the protonated version of our acetal. And then lose that proton. And get what's a full acetal. Someone in the chat asked what's the name of this mechanism. It should be like acetal formation or acid catalyzed acetal formation. So an acetal is when you have 2 ethers in the same center. So we have 1 ether here, another ether here. The hemiacetal is where we have just 1 ether. And the other one is an alcohol. It's really just like a halfway point on these reactions. Sometimes you can freeze them there, but it's very difficult. Okay, So you can also do this with a diol and make what's called a cyclic acetal. Give you guys a second to keep writing this. So we're doing the same thing. We're just going to have both of the oxygens that attack come from the same molecule. So we'll pick up a proton, make our H plus or our protonated carbonyl. From this point here, we can come in and do an attack on this carbonyl. We will get our protonated hemiacetal. I'm just going to draw an arrow with H plus leaving instead of having this get picked off. You guys are welcome to do that also to give us this acetal here, or sorry, hemiacetal. This one will pick up an H plus. It can leave. And then this is where this is going to be a little bit different. So now this oxygen is going to attack. It's going to be the closest one in terms of proximity here. We're going to make a 5-membered ring out of this. So 1, 2, 3, 4, 5. Lose that last H plus. To give us a cyclic acetal. This is going to be really useful because these can act as protecting groups. For that are selective for aldehydes and ketones. So for instance, if I have this and I want to do a synthesis and make this here, taking a look at them, we probably did some sort of a Grignard, added these two ethyl groups onto here. We try to just do the Grignard. It'll also add to this carbonyl, which means we would have needed to protect it. our previous method of protecting would have been reducing this with sodium borohydride, adding TMS chloride, doing the Grignard, taking off the TMS chloride, and then reoxidizing. That's a lot of steps. If you just want to preserve your carbonyl here, we could just throw in H plus this diol. This is not a carbonyl anymore. It's really, that's hard to read. It says not carbonyl. It's really just two ethers that are directly attached to each other. So if I throw in a Grignard, it's not going to affect these at all. And then if I throw in H plus in water, I can reverse this. And get the product. We'll do a lot of these on Friday. Right now, I just want to give you guys kind of an introduction as to how to do them. But yeah, you can also use these as protecting groups. All right, so doing a little bit of review as to what we've gone through so far. We've had H plus and H2O. Let's just make these diols here. We throw in ethanol and H plus. Let's do propanol. Make it a little different. This will make an acetal. We throw in a diol. We'll do a different ring size. So your ring size is always going to be the number of atoms for your diol plus one. So it'll be 1, 2, 3, 4, 5. And then you're going to get a 6th carbon here from where your ketone was. So this will end up giving you, this is kind of your base structure. There's 3 carbons in the middle. So 1, 2, 3 here. This will give you a 6-membered ring. Your book spends a lot of time talking about the sulfur version of this. I think it's pretty straightforward, so I'm not going to overly cover it. Basically, anything you can do with oxygen, you can also do with sulfur. So if we have SHs instead, you're just replacing those oxygens with sulfurs. It works the exact same way. The sulfur is nice though, because it lets you do a reaction where you can fully reduce this off. So we're going to throw in a reagent called Raney nickel. And this is going to let us generate butane. All right, so that's the oxygen and sulfur reactions. There are some amine reactions, which they follow the same general pathway. They're just going to have 1 or 2 different steps at the end of it. So if we take a primary amine, like ethylamine. So we're gonna have H plus in solution. We're gonna have this primary amine, which has ethyl attached to it, or it's amine with ethyl attached to it. Our first step is going to be exactly the same as it was before. We're going to pick up an H plus. The first couple of steps are going to be the same. Our amine is going to attack. We're going to need to lose a proton. Off of our nitrogen. We're going to pick up that proton on our oxygen, just like we've been doing. And this is where it's going to change a little bit. So instead of just losing this water, what's going to happen is our nitrogen electrons are going to come down. And we are going to create a new double bond, kicking out water. To give us this protonated carbonyl here. We can lose the proton. And we are going to generate what's called an imine. So if you take a look at what you started with, essentially what's going to happen is this nitrogen and the carbons that are attached to it are going to replace this oxygen here. And we're going to lose the two other protons that were on it. So we still have a double bond. It's now to this nitrogen instead of the oxygen. And it still has that ethyl group on it. All right, if this is secondary, it's going to complicate things a little bit more. 95% of the steps are going to be the same, but the last step is going to have a little bit of a variation to it. So if I take our acetone here still, throw it in with H plus, and now diethylamine. So we have two different substituents. This is now secondary. The vast majority of our mechanism is still the same. We're going to pick up a proton. We can have our amine come and attack. We'll lose the proton from our amine here. We'll again pick it up on our oxygen. our nitrogen can come down and kick out this water again. And we'll generate an amine. And this is gonna be where we're gonna get a slight variation. So if we take a look at this compared to what we had before, on the last one, we got to this stage here where we made the amine that was protonated. We had a proton here, which is easily pulled off. For this secondary one, we have 2 carbon groups, and they are not going to break. So instead, what will happen is your amine that you already have. So you have ethylamine solution, diethylamine. This is a base. It'll pull off one of these adjacent protons. You'll do essentially a tautomerization and make what's called an enamine. So we shifted that double bond from being attached to the nitrogen to now being 1 carbon away from it. Everything is now neutral. And this is going to be our final product from these. All right, so doing a little bit of a review of these, if we take ammonia, which would be our unsubstituted version, so H plus NH3, we're gonna get an imine that looks like this here, where we're gonna keep one of those 3 protons for this one. We throw in a secondary, or sorry, a primary one now. This was not substituted at all. So let's do isobutyl, mix it up a little bit. Isobutylamine here. We'll keep that isobutyl, we'll lose 2 of the protons. We can generate this imine. We have secondary. We would originally make this isobutyl imine, which is positively charged. This is going to do a tautomerization. We're going to shift that double bond over. To generate the enamine, which is going to look like this. When we're doing these, the nitrogen that's acting as the base, so this diisopropylamine here, this is a large base, which means that when I have different substituents, let's make this a little bit more unique. I'm going to throw this on here instead. Do the same reaction. H plus amine. We would originally make this, when we do our tautomerization, we have two different possibilities. We have this H and we have these three H's. And because this nitrogen here is going to be a large base, it's going to be selective for that more or less substitute position. So it is going to pull off this proton here as opposed to the one on the tertiary center. And we're going to get this in enamine. All right, I'm going to talk through a couple more reactions which follow the same principles. You do hydrazine. So H plus NH2 NH2. We have two amines on here. We're actually just going to ignore one of them. We're going to treat this like it's just a primary amine here. I'm not going to go through the whole mechanism. You're just going to get a normal enamine as if this was a CH2, CH3 over here. We're just going to kind of ignore one of our two amine groups. Hydroxylamine is going to be the same. Okay, so we have NH2OH. Between nitrogen and oxygen, nitrogen's the better nucleophile. So because of that, we're basically doing the exact same thing as we're doing above. You're going to ignore this OH, treat it like it's just a substituent. And whoa. Hopefully this didn't delete everything. Nope, we're still good. Okay. So we're going to make what's called an oxime here. Same concept as before. We're basically treating this OH like it's CH3. And we're just going to ignore it through our mechanism. A couple other reactions. A lot of them you guys already know. So if you take ketone, and we are going to pause to this. Oh, I think we're good. All right, so from here, we could throw an LAH. It's a reaction you guys should know at this point. And water. This will let us reduce this to an alcohol. We could throw in a Grignard. The one we didn't really talk about is you can actually do the same thing with a nitrile. So if you take KCN and HCN, so acetonitrile, as your solvent here, you're going to do an attack on your carbonyl just like you would with a Grignard. And add CN to it. So taking a look at all the reactions you can do with a carbonyl. We start with acetone. Throw in H plus H2O. Oh, someone wants me to show the last one real quick. All right. H plus H2O, we can make the diol. We throw in a H plus and an alcohol. We can make the acetal. We can do the cyclic version of this. We could also do this with sulfur. If we do it with sulfur, we can throw in Raney nickel to reduce it. We can do amines. This is a primary amine. A secondary amine is going to make us an enamine. We can throw in hydrazine. Or hydroxylamine. And then our last couple reactions, throwing in LAH. Water lets us reduce this. Grignard lets us alkylate it. And then a nitrile. This is that a nitrile to it. So KCN, HCN will let us make the nitrile. All right, on Friday, I'm going to talk about two more reactions. There's a Grignard, or not a Grignard, a Wittig reaction, as well as the Bayer-Villiger reaction. And then we're going to do a bunch of synthesis problems and maybe start reviewing stuff for your exam. So I'm going to let you guys go early today, and I will see you guys on Friday. Question in the chat. Thanks. Okay.